Okay, let's pick up from where we left off last time. So last time we talked about how we stack different matrix multipliers and form multi-layer perceptron. And then we talked about convolutional neural network. So compared to MLP, convolutional neural network doesn't require that we explode the input space. So for example, if you have image input, you can take the image input as is and preserve spatial information, and also reduce number of parameters by weight sharing. But in contrast, your output activation is going to be very large compared to MLP. And to make CNN work, we introduced various techniques, pulling layers to reduce spatial information for the activation layers, and different activation like 10H, sigmoid, ReLU, and very important, weight initialization. This is still used today. And normalization, we talked about batch norm, instance norm, group norm, layer norm, etc. And now let's talk briefly about regularization. So here, a disclaimer is that we're scratching the surface of regularization. All right, so what do you mean by overfitting? So there's underfitting and overfitting. So we talked about this briefly last time. So anyone want to volunteer? What's the difference between underfitting? What's underfitting and what's overfitting? Sorry, can you simplify a little bit? What's underfitting? No. Yes? Right, so underfitting is when training loss is still high. So you don't even learn from the training data, let alone generalization to previously unseen data points. Overfitting, on the other hand, your training loss is small, but don't generalize to previously unseen test data. So to draw the analogy, which is not perfect by the way, underfitting is you obtain previous year's exam and you don't put enough effort, so you don't even know how to solve the previous exam, even if it's given to you. I don't know, because you play too much game or drank too much. Previous exam, you don't even know how to solve it. And overfitting, okay, here, okay, you know perfectly every single step in how to solve previous exam. Okay, you basically memorized all the details. But if I change the exam questions, then you completely fail because you didn't learn the underlying concept. You basically just memorized the previous year's exam. So in machine learning, the whole purpose is to generalize the previously unseen test data. So this is slightly tangential, but machine learning 101 the very basic is, let's say somebody gave you data, training data, and you want to design the neural architecture and define a loss and start training. And you split the data. Maybe you want to do k-fold cross-validation, meaning you're given the data and you divide it in multiple chunks. So you train here, test here, and you train here and here, and test here, etc. So the very basic is here you need to be able to overfit. First thing, step one is make sure you can overfit to the training data. Otherwise, there's no hope of generalization. You first need to at least be able to memorize the overfit, the training data. That's the beginning. If you don't, multiple things. Maybe your model is too large compared to the number of data points you have available. So either go collect more data or decrease the number of parameters in your training, in your architecture. So make your model smaller. Then try again and make sure your training loss goes down like this over time. Then we can worry about regularization later. If you don't have a nice training curve that goes down over time, then you don't even need to worry about regularization. That comes after we have successfully decreased the training loss enough. So that's step one. Step two, okay, your training loss goes down, and you check your loss on the validation set. And here, y-axis is the loss, so smaller the better. Here, the y-axis is the accuracy, so higher the better. All right, so you get a miserable performance. So say this is a binary classification problem. Meaning the output is either 0 or 1. And you get 50% validation error, validation accuracy. What does it mean? Assuming the label distribution is uniform, which is often never the case, but let's just assume the label distribution is uniform, meaning in your test data, there's equal number of ones versus equal number of negative one labels. And you're outputting something and you get 50%, meaning it's a random chance. So outputting a random number. So here, the gap between the training accuracy and validation accuracy, that's called the generalization gap. So how do we make the model to learn more general concept? So one way to do this is to use regularization. And we have already seen L2 regularization, I think. So this is often called weight decay. Sometimes it's called L2 regularization. They all mean the same thing. Okay, and here we have our, in this case, hinge loss plus some lambda times regularization function. And this is called the regularization hyperparameter. And I would say the default choice is to use L2 regularization. And L1 regularization encourages sparsity of the solution, meaning after you train this, there's going to be lots of zero in theory, but not so much in practice. You need to clip small values to zero after gradient step. But in theory, this will encourage sparse solutions. And elastic net is a combination of both L1 and L2 regularization. So there's a deep theory about generalization gap and why L2 regularization enforces simpler models and induces simpler models that generalize better, etc. But it's out of the scope because we have so much to cover. And another way to do this to achieve regularization is to use dropout. But a disclaimer is this is not used very often these days. But still, we need to learn this. So what it does is it randomly sets some activations to 0 in each 4 pass. So you do a 4 pass, and these edges are weights, and these nodes are activations. So what you do is you randomly just drop some of the activations, and that's it. And there's a hyperparameter on the percentage of, or the probability of dropping activation. So sounds like an insane idea, right? You're playing gradient descent, and during 4 pass, you randomly set half of the activations to 0. Doesn't sound very sensical, right? But when this came out, it really improved the generalization performance of really, really deep CNNs. And here's how you implement it. So during training step, this is the vanilla version. So P.5, that's probability of keeping a unit active. So here's the example 3-layer MLP. You take your input X, multiply by the first FC layer, FC fully connected. Matrix multiply, all same, they mean all the same thing. So you matrix multiply W1 with X and apply some bias and apply value. That's value, right? And then you create your dropout mask. So you create a random number. If it's less than P, you drop it. And you multiply your first activation with the dropout mask to drop whichever is not selected. You take your H, do the same thing again. Matrix multiply with the second layer weight, add bias, value, create the mask, apply the mask, etc. So, by the way, this is how you sample from Bernoulli distribution. So Bernoulli distribution, you have 2 binary outcomes with head probability given. You create a random number from 0 to 1. Random uniform number here. And you have your head probability P. And you just check if the sample lies here or here. That's how you sample from bias coin. All right, so there is some interpretation, but this is just intuition, but I don't know, I don't really like it. So let's really think about what happens during test time. So it randomly masks activations to 0, and let's represent the model as F. Then for input X and a given random mask Z, your output is going to be Y. And during test time, you don't want any randomness. You want to start deterministic behavior. Say you deploy your model on a cell phone, you take a photo. Each time you upload the same photo, you expect the output to be the same. So the sensible thing during test time is to take average over the randomness, which is the mask Z. So this integral is difficult to solve analytically because this function is really complex. So let's look at a very simple example. So given two activation X and Y and some weights W and W2, the expected output will be with training dropout probability 0.5. It's going to be average of all these 4 different types of outcomes, right? All of them survive, only one of them survive, or none of them survive. So that's going to be 1/2 of what it used to be. So this here, these guys are same. So during test time, we don't want any randomness. We want deterministic behavior. So all activations will be kept alive. We're not going to drop anything. But if you look at the expectation, it's going to be that we're going to be expecting output attenuated by the dropout probability. So we can do 2 things. We can either account for this during test time, so multiply by inverse of the probability so that the expected output matches the training output, or we can bake this in during the training time. So during training time, when we apply the mask, we account for this attenuation as we apply the dropout. That's better because we always want the inference code to run as fast as possible. Because training time can be slow, it's okay because we only need to train once. Once we finish the product and ship it, we want to run it. We want it to run as soon as as fast as possible, because for best customer experience. So we want to put less computation burden during inference, and if we have a choice, do as much computation during training time. Okay, so all right. So how do we do this? So as opposed to accounting for this attenuation at testing time, it's better to do this during training time, so that the training, so that the test code doesn't change, and saves some computation, although not that much in this case. So you're given X. This could be a flattened image or whatever, and apply first, matrix multiply, add in bias, ReLU, take this guy, apply the second matrix, second bias, ReLU, apply the third matrix and ReLU, and that's the output. Oh, and it's important to note that you typically don't apply these nonlinearities like ReLU to the final output of the model. Okay? What I mean is you don't do this typically. This is a really bad idea. All right, so dropout used to be famous when people went really, really deep in stacking the layers for convolutional neural networks. but modern architectures don't really use dropout. So the common pattern is during training time, you add some kind of randomness, and during test time, you average out the randomness. So we're going to see more instances of this when we also talk about data augmentation. So the idea of data augmentation is you only have limited amount of data. So to show to the model more diverse input data, you want to perturb the training data realistically, in a realistic way. So on the fly, we can generate almost infinite amount of variations to the training data. It learns to generalize very well if you apply these augmentations. All right, so I think this lecture is going to be very, very long. So I don't expect to finish everything today. So I have 91 pages. So maybe we can do about half today. So here, we're going to, in lecture 4, talk about sequential modeling. So when you input data in a sequence, not in bulk like images, you need different architectures that can handle that. So we're going to talk about a very simple model called RNN, and then LSTM, and then we're going to talk about attention and transformers, which is the core backbone of modern LLMs. All right, so we talked about feed-forward neural networks. So it's typically one-to-one. For example, for image classification, you have image input, and it outputs probability of the labels here, right? It's one-to-one. But in order to deal with more complex data and more complex tasks, we need different architecture. For example, we want to do, let's say we want to do image captioning. We want to input an image and output the description of the image. So we want to output a sequence of words from the model. So here, the relationship is one-to-many. How about video classification? You now have sequence of image frames as input that constitute the video, and you have a single output, which is a label of the video. It's a sports video or academic lecture video, etc. You also have many-to-many. For example, for translation, you are input a sequence of words in English, and you want to output a sequence of words in Korean, then that's many-to-many mapping. Or you could do something more complicated. You could do a per frame video classification. So you're given a sequence of images, and you want to output a sequence of labels individually per each frame. And here, the first model architecture we're going to learn is RNN, recurrent neural network. So the idea in RNN is you have this internal state that is being updated as we process sequences of data. And this internal state or hidden state is you take the previous hidden state, take the current data, and apply some operation, and that's going to be updated hidden state. And here, you do not want to use different W's per each sequence because they will have too much parameter. So you want to recycle and reuse the same W all the time. For example, if you have, if you're dealing with videos, you might have a sequence of, I don't know, I'm just creating some random number, like 10K frames. Then you don't want to use 10K weight matrices, right? Because it's going to blow up your memory. So you want to reuse the same W for different inputs. And it typically has 3 matrices. WHH, it takes a hidden state and updates, it applies to the hidden state. And WXH, it takes the current sequence XT and applies this matrix. And you also have some bias. And you have nonlinearity. And that's going to be your updated hidden state. So you take previous hidden state, current input, apply WHH, WXH, add in some bias, apply nonlinearity. That's going to be your updated hidden state. And you take the updated hidden state. If you want to produce an output in this current time step, you don't necessarily have to. But if you have to, then you have another third matrix, which takes the hidden state and outputs something. So, yeah, already explained it. So you want to reuse the same weight matrix at every time step to be primary efficient. And if you're dealing with many-to-many, then you take the current input, apply some matrix, and collect the previous hidden state, apply WHH. Here you'd apply WXH, and you have your updated hidden vector. Here you would multiply WYH to produce an output, and it repeats. And then per each produced output, you'd compute the loss, whether the currently emitted output is correct or not. And sum of all these losses over multiple time steps, that's going to be your final loss. So this is for one single example sequence, and you repeat this over multiple sequences and apply gradient descent to optimize over your 3 primary matrices. Many-to-one, for example, for a video classification, you would input sequences of frames and keep updating your hidden state. And upon computing the final hidden state, you would apply WYH to produce the final output. Similarly, for one-to-many, you're given some input and you want to describe. So, for example, you're given an input image and you want to output the description of the image, and these are going to be one-to-many computation graph. And for example, for sequence to sequence, there are many variations, but one thing you can do is many-to-one. So you process the inputs one by one and condense all the information into HT. And from HT, you'd start decoding its translation, for example, one by one. And here it probably would make sense to use different weights. One to understand this language, one to decode it into Korean or something like this. So this is very simplified example for language modeling. So you want to do character level language modeling, and here first thing you need to do is define the vocabulary. Here we have a very simplified example where we only have 4 characters, H, E, L, O. But if we want to do character level, then we'll probably have 256 characters in the vocabulary. And this is typically called dictionary as well. And given each character inputs, it's supposed to output the next character that follows the preceding character. So given a sequence hello, we input the first character H, and it's supposed to output probability distribution on their characters. So here, I don't know, H, E, L, O. Something like this. And we want the probability for the correct next character to be higher than the probability, not necessarily probability, it's unnormalized. So we want the score for the next character to be higher than the score for the other characters. That's the loss that's going to be implied here. And then you would insert the second character, E, from the sequence, do some computation, and it's going to output a score here. And we're going to look at the score for the correct next following character. And we want this to be higher than the score for other characters. And it's going to incur some loss here, and etc. And you'd add up all these small losses, and that's going to be your loss function. So it learns to predict the next character. And yeah, I already explained this. So here you insert H, and here you output a score for the next character. And here you're given, you input the next character E and compute it again. But the idea here is in RNNs, the previous hidden state update already encodes information about the past. So this guy already has the information that the previously encoded inserted character is H. Through computation here. Okay. And you repeat. And I think in about 2 lectures, we're going to start building LLMs together. And there we're going to start from very beginning, which is we build our own dictionary and tokenize the data set and etc. Okay, so if you imagine the backprop of this computation graph, then you have, let's say you want to do many-to-many, and you have these individual losses all the way to the end, and some of the losses are going to be your final loss. So in order to backprop here, you first need to for pass through the entire sequence until the end. You first need to go all the way here so that you can add this guy and compute the loss. And then, given the computed loss, you need to backprop all the way back to the beginning. And it's going to take a lot of memory for long sequences. So there are multiple things you can do to walk around this. One is called truncation. So what you can do is you run forward and backward through a chunk subsequence instead of a whole sequence. So as opposed to going all the way, you do a forward pass on the chunk and backward pass on the chunk. But what's important is, in order to initiate the next chunk, you need to compute this guy, keep it in the memory to initialize this RNN state. Okay, so just think about the forward pass. Here, there's no initial state. But from the second chunk, in order to compute this guy, you need ht minus 1 somewhere in the memory so that you can initiate this. That's the only caveat, and rest of them is pretty straightforward. You for chunk 1, backward chunk 1, keep the last hidden activation to initialize the RNN state, for chunk 2, backward chunk 2, etc. All right, so people have tried this on the sonnet from Shakespeare, and the results are very good. So in the beginning, it outputs some random characters, but after you apply some substantial amount of gradient descent, then it starts to output something that makes sense. So how do you do inference? Typically, there's a... we're going to talk about this later in about 2 lectures. So when we construct a vocabulary, there's a special token called beginning of sentence token and end of sentence token. So per each sequence, it's pre-padded with beginning of sentence token and post-padded with end of sentence token. All sequence. So during inference, what you do is you first insert here beginning of sentence token and start decoding here. So here, take the one with the highest score, so this guy, and sample from this distribution. You can do multiple things. This is in the end of the lecture today. There are many ways to do this. One is just greedy sampling. You take the one with the highest score. That's going to be, I guess, O. And insert this, get the score. This guy, again, has high score. Sample the one with high score. Here, this guy has high score. It's going to be L, etc. And beginning token is always going to be beginning of sentence token. That's how you do inference or a generalization. Or you can just do a sampling. So since you can interpret this as probability distribution, you can normalize this with softmax and sample from this distribution. And let's say we sample this guy, gets inserted here, and etc. And when do we stop? We stop when we sample end of sentence token. All right, more about this later. And you can also do many different tasks. You can train it on somebody else's C code and make it output a C code. And you can also do image captioning. So you can insert an image to a CNN, get a hidden state so that the dimensions commute with the internal state of RNN. This is going to be the initial state. And that's going to be the seed to update the first hidden state. And then you start decoding. So this is the beginning of sentence token. You insert this special token and sample from the distribution here. And straw, insert this, followed by hat, insert this, and you stop when you sample end of sentence token. So here, why do you need 2 models? Because here the CNN is to condense the image into a hidden vector, so we can initialize and pass in the information of the image to the RNN here. And RNN is going to be responsible for handling the image input or representation of the image and start generating text that describes the image. And same thing for image captioning and etc. So now we're going to talk about LSTMs, which in practice works much better than RNN because of this problem. So here, let's think about the RNN structure that we talked about. This is the update formula. You take the previous hidden state, current sequence input, multiply respective matrices, add in some bias, apply 10H. We can write this equivalently as a stacked input of previous hidden state and current input XT applied by some matrix W plus some bias. So as we keep processing these inputs over and over, it's passing through matrix multiply of W and repeated 10H. So if the largest singular value of this matrix W matrix is greater than 1, then if we keep repeating this matrix, then we're going to have explosion to positive infinity. We're going to get an NAN. This is easier to handle because we can simply scale the gradient if the norm is too big. So, for example, given a gradient, we compute its L2 norm. If it's greater than some threshold that we set, we can normalize it with its own norm. Because direction is more important than the magnitude for the gradient. But the bigger problem is if the largest singular value of the matrix is less than 1, then it's going to go to a very small number and we're going to have vanishing gradient. So this one is harder to bypass or handle. So we're going to change the architecture, and this is the LSTM architecture. So previously we had this vanilla RNN where we stack the inputs and multiply some matrix. Here we're going to first create this thing called cell state, and how you compute the hidden state is you apply 10H to cell state and do element-wise multiply or gating with output cell, output gate. So here we converted the matrix multiply with element-wise multiply. And let's look at how the cell state is computed. We take the previous cell state, do gating with forget gate, take the gate and input gate and do element-wise multiply and then add them together. So here, there's no matrix multiply. Okay, how are these four guys being computed? This we just explained. You take the input, multiply matrix, and apply sigmoid here. That's going to be input forget output gate, and apply 10H to output a gate. So pictorially, it looks like this. Previously, we stack X and H and multiply this matrix W for the vanilla RNN case. For the LSTM case, once we apply this matrix, we apply these 4 nonlinearities to compute I input, forget, output, gate, and then the cell state update doesn't require any other matrix multiply, and hidden state is computed from the cell state. So if you look at it pictorially, you have this current data sequence and previous hidden state and previous cell state. And what's nice about this is if you look at the top row here, the cell states, when you pass cell state to a next cell to process the next sequence, updated cell state doesn't require matrix multiply. So it's less prone to this gradient flow problem that we saw in the vanilla RNN case. So the cell states can pass information from one state to another without matrix multiply. And the addition of information from the next sequence, yes, you have a matrix multiply, but it's added to existing cell state. So as opposed to vanilla RNN, where in order to pass H, you need to multiply this to produce next H. Here, you have uninterrupted cell state transfer, and you are only adding to the cell through matrix multiply. So gradient flow in the cell states, they don't get any matrix multiply, so we don't have that problem. And people also have tried, and okay, if you have a question, okay, why does this work? And is there any theory behind whether if this architecture is optimal? No, short answer is no. People have tried multiple things and this worked. Are they still using LSTMs these days? No. All right, so people also have tried multi-layer RNNs. So okay, so what are they using these days? Two things: transformers, which we're about to cover next lecture, I guess, and state space models, which is less popular than transformers, but I think we'll cover this if we have time. So people also have tried stacking the RNNs. So here, typically you process sequence data, update H's, but you can also stack RNN depth-wise. So given the current hidden state, do some matrix multiply again, and do another round of processing, and keep going until before you produce the output. Right? That's the point of deep learning, right? You increase number of parameters and in creative ways with nonlinearities placed in important locations so that it doesn't collapse into one linear model. But empirically, it didn't provide much benefit. I think we're going to come back to this towards the end of the lecture. So you can also apply reinforcement learning to find a different architecture. So you can explore the search space of neural architectures and learn an RL agent that proposes the one example neural architecture, and the reward is going to be how well it performs if you train the proposed network on a data set and look at the validation or test loss. That's going to be the reward. Based on the reward, you'll be proposing a next neural architecture, and it's going to incur a reward once we train this proposed network on the data set and observe the test loss, and etc. If you repeat this, you're going to be able to recover, you're going to be able to propose a network that presumably works better than what already exists. So this type of research area is called Neural Architecture Search, or NAS. So yeah, I'm going to skip these so you can read it on your own. Okay, so we have about 20 minutes, and let's talk briefly about attention module. So let's think about what we discussed so far today. So we talked about sequence-to-sequence modeling with RNN, LSTM, encoder, decoder. And encoder reads input sequences, updates the hidden states, and final state summarizes the entire input, and from that you can decode another sequence if you like. And what does the decoder do? So this is a sequence where let's say we want to do machine translation. These are in English. You want to apply RNN to get a single hidden state, and this is going to be the seed for. This is English RNN, Korean RNN, and it's going to start outputting S1, S2, SL. So to decode these translations, you have this condensed information about the English input and previous hidden state in the Korean RNN and the correct output. So one problem here is the entire input sequence must be compressed into a single vector C. So if you have an extremely long sequence, so say you are inputting, I don't know, 10,000 page PDF file. You're uploading your 10,000 page PDF file, I don't know, textbook or something into your ChatGPT, or you want to ask ChatGPT to review your project report, which is I don't know, about 20 pages or something. It's going to be a very, very long sequence. But if we use RNN structure, then we are asking it to condense all that knowledge into a vector, which is typically of size 512 or 10,024 or something like this. It's not very long. So if you are dealing with long sequences, we have information bottleneck. And actually, the decoder cannot really access the earlier tokens because everything is compressed into a single vector. So the idea is, instead of a single context vector, you want to allow a decoder to look back at all encoded states. You want to propose another architecture such that during decoding, it has explicit access to all previous tokens, as opposed to decoding it from a single compressed vector. So here is the self-attention layer module. So this is neural architecture, and X is the input. So NX is batch size, DX is some hidden dimension, or if this is front-facing, meaning if this guy is facing the data, this is going to be you can interpret it as number of words in the dictionary or number of vocabulary. So given and x1 is the first, you can interpret this as first token, second token, third token, or first character, second character, third character, or first word, second word, third word. Doesn't really matter. Just some sequence of input. And the key, from X, we introduce three parameters here: key matrix, value matrix, and query matrix. Notice the key and query, they commute, they have same dimensions. So these are input. And given the input, we're going to compute the three activations: query vector, key vector, and value vector. Okay. Query, key, value. From these, let's just first look at the query and key. We compute Q K transpose, or outer product of query and key, and normalize it with square root of dimension. That's going to be these E's here. We call this similarities. So now, every token sees another token through the similarity computation. Once we compute the similarity, we compute softmax in dimension 1 so that we output nx times nx, or number of tokens by number of tokens, or batch by batch attention score. So these are attention score. Once we compute the attention score, we are now ready to emit the outputs. So here, you take your value activations, multiply by attention, and that's going to be your output Y. So during the following lectures, we're going to implement all these details together. So you don't need to memorize this. I think you will memorize this because you're going to do homeworks and stuff. So one thing then you need to, and we're going to go deeper in this. One thing you can notice is in RNNs or LSTMs, if you permute the input, then it affects the output vectors significantly because different order get encoded in the hidden states, but in the attention module, if you swap in the tokens in some random order, then it's just going to compute the key and query in that specific swapped order, and but just permuted. So you're going to have the same numbers, but in permuted order. self-attention layer is permutation equivariant. So in order to work around this, what you can do is concatenate the input with something that's sensitive to the position of its original sentence in the data. So this could be some fixed function or learned table or something like this. And well, what happened? I think I accidentally closed it. Okay. So in about 2 lectures or 3 lectures, we're going to implement what's being used these days. It's called rotational positional encoding. And more details to be followed later. Another thing is during inference, if you think about what's happening during inference, let's say we want to do decoding. Here I explained every token can attend to or can look at other tokens. They communicate here through this stage. But during inference, we're generating tokens one at a time. So when we generate, for example, ith token, it only has access to token 1 through I-1. It doesn't have access to the future tokens because it's not generated yet, right? So we want to prevent during training looking ahead in position. So that's called masked self-attention. So here, basically, we want to set these scores to negative infinity and the corresponding attention scores to 0. So token 3, for example, can attend to, if it's predicting itself, everything. Position 2 can attend to itself, and 1 before. Position 1 can only attend to itself. So these special locations are preserved to negative infinity for score, zeros for attention. We only compute the lower triangles so that it can work during inference, because it must not have access to the future tokens. Also, in transformers, we want to have the same architecture repeated over multiple heads. So it's called multi-head self-attention. And you collect the multi-head outputs to produce the next set of inputs. Because we're going to stack this. So this is going to be one of the core modules in the transformer. And we're going to stack this multiple depth-wise. So before we go deeper, let's first take a step back and contrast different architectures that we talked about. We talked about RNNs today for processing a sequence of inputs and outputs. The pros is it's theoretically good for long sequences, and compute and memory for sequence of length n, it's O of n. Compared to self-attention, where it's O of n squared to compute, and O of n memory for sequence of length n. And this guy is not parallelizable. You need to process one input at a time and decode one at a time. So it's really slow. Another thing you can do is do convolution in 1D. So upside is you can parallel process the inputs. So here it's doing convolution with receptive field of 3. It looks at 3 neighbors to produce 1 output. This is called the receptive field. But in order for some output to have other tokens in field of view, then we need to stack this depth-wise, so that if this guy looks at 3 guy and here it has larger field of view, so you need to stack this convolution depth-wise a lot in order to give this enough receptive field. So when you want to produce outputs that's really long, that needs to attend to really long context, then you need to stack this really, really long depth-wise. Self-attention that we learned today, it's great for long sequences because each output has access to all past tokens or representation of the tokens explicitly, and the computation is highly parallel during training. And it's very expensive because here we're basically taking cross product of the key and the query as a query and key. So it's n squared to compute and on memory for long sequence of length. And addressing this is a very, very active research area. So how can you propose a next self-attention module or next architecture? So it still has good performance, but has less compute and memory during training and inference. Because during inference, you need to, so say you're processing, 100K tokens, and you need to have in the memory 100K by 100K similarity and attention score, and all these query and key vectors. So you're going to have activation for every single token times 3 because you need to hold in the memory the values and keys and queries. Very, very expensive. And I think the last lecture is going to be dedicated on how to delete not so important token, not so important KB caches, or not so important key and value activations. That's called KB cache compression. Very active research area. And let's see, how many slides do I have? Okay, I have endless number of slides. Okay, let's see how far we can go. Okay, so this is the transformer block. First, it takes the tokens as input and computes the self-attention that we just talked about. And then it applies the layer normalization. We talked about layer normalization in the previous lecture. So just to remind you, given a set of activations in D dimensions, and it computes a scalar, mu, and sigma, which is the mean and standard deviation. So you subtract the mean and standard deviation. So these are scalars. And then this is learnable parameter, gamma and beta, in order to give it a chance to recover identity. All right, so once you compute self-attention, now you apply layer normalization. And then per each token activation independently, so this guy outputs our activations, and you apply layer norm, and then each activation is applied some FC layers, typically 2 or 3 layers of matrix multiplies, and then you reapply layer normalization to produce output. So this is one transformer block, and we're going to implement this together during the hands-on lectures. And you stack this block many, many times to construct LLMs. And these days, they stick this in right before the residual connection and many other tricks, but we have that in the slides. So one interesting thing is across different tokens, they do not communicate unless they're in the self-attention stage. So they only communicate with each other during self-attention stage. Layer norm, they do not communicate. MLP, they do not communicate. This MLP is only applied to the specific token. Okay? So each token gets processed independently unless you are in the attention stage. Okay, it's very important to note in MLP, the tokens do not communicate. So we can parallelize this computation. So it's highly scalable and it's highly parallelizable. Everything except self-attention is highly parallelizable. So like I said, self-attention is the only interaction between the token vectors. And yeah, you have one transformer block, you stack it depth-wise, and that's the core foundation of the transformer. So in the original paper, they had 12 blocks of transformer, and each transformer block had, each self-attention block had 6 multi-heads, and the query vector dimension was 512. And like I said, layer norm and MLP layers works independently per each token vector. And we're going to build this together during the lecture. And also, you're going to have homeworks. Yeah, so unfortunately, I think we have to pick up the remaining material next time because we have so much detail left that I don't want to go into and cut in the middle. All right, thanks.